So let n be the total number of turns. N is number of turns here. Where the field will be confined only to this particular region A, like a width AB, that one. The field will be confined only in this one. What about field here? Will be zero, field will be zero. Only for the circular region, the field will be confined. Yes, in applications, we do need such a fields. That's why they brought this one here. What is that red color things? It's called like a core. Later, you can understand this called like a core. On that core, it will be made up of ferrite material. Good example of ferrite material, nickel, cobalt, and iron. They are the ferrite materials. That one. So what is a wire? There's a copper wire, no? And copper wire is wound on iron. Short circuit should happen, no? So what actually happens on this ferrite core? I'll provide an insulating coating. Then I'll take copper, I'll wound in. The once if I when I wound one turn, I'll apply that with brush, that insulating layer like this. Then I'll wound another turn. Then again insulating layer. Again I'll wound the turn. Already I said for solenoid. To make you understand, we are showing gap between the turns. If you show like this, the flux will escape from here. The B bar will escape from here. So for that not to happen, the turns are wound very closely. Is it okay? There's not a correct diagram. The turns are wound very closely here. And how come that iron core? That one, sir, the core is made up of iron. Then there's a copper wire. So again, you just assume a ring bangle, girls, the bangle, that one. So let it be made up of iron, bangle made up of iron. Give insulating coating on it. Then wound copper wire on it. And between the turns, there's been insulating. This is actually the basic construction of the toroid here. Now we have to get expression for field, where the field will be present only in this region. So I'll put it. So there's the field will be present only in the cylindrical region of diameter x. And how that cylindrical region is there? Because it will be so I'll in a simplified way, I'll just shade it. Only in that yellow color region, the field will be confined. The field will be confined only to that yellow color region. We have to get expression for the magnetic field. So shall I assume Amperes Circuit Law? Yes, there's the best thing which will help us a lot. So I'll take help of Amperes Circuit Law. I will draw a Amperian path. Are you seeing a green color dotted line? Green color dotted line. the what is that? There's a Amperian loop or path, anything you can write. So, and let this be how B bar. So if you look at the current everywhere, so here I'll show the direction of current. Current should be like this. I. So B bar should be somewhere like this. And show current I. And the B bar, show it 2-3 places. It'll be easy for you. The current will be like this, and B bar will be everywhere. The B bar will be tangential to the Amperian loop. This is the DL. So how B bar and DL bar will be everywhere parallel, no? It will be. So I'm showing almost at a few places. This should be the direction of B bar. Okay, directly go for integral of, and B is constant at all points, so straight away I write like this is equal to mu naught. Now how many turns it will enclose? Total n number of turns are the count it no. You can count it no. 1, 2, 1, 2, 3, 4, 5, 6, 7. N number of turns are there. So what is the total current? Current I is, you look at this particular, so don't take this particular thing. So here current I is entering no. Here, look at this one, I, everywhere it's entering. So Ni is what I should take. Don't draw here. What is a B bar? I think the Amperes law will really help you a lot. If you draw an Amperian loop here, what will happen? How much of current high enters, that much it will leave, no? So altogether, what actually happening here? If you take the same diagram. No, there are this will be outgoing. Where is Amperian path? Amperian path is here, no? Take this is R, and this is DL, and B bar is like this. I think I'm giving enough explanation for you now. So that green color strip is what? The DL. Everywhere if you want to show it, this will be B bar. Okay, now write it. So what should be the, how much of current it will enclose? So how many are there? I think eight high, that one. So like that, how many are there? Ni. And what will get? If you integrate this closed path, dl in closed path, 2 pi r. So finally, what is B bar? Mu naught Ni by 2r. Strictly, what is the now you can ask question, sir. I will take, I'll draw Amperian path here. From Amperes circuit, it's quite clear, no? What is the net current enclosed? Net current element plus I minus I plus I minus I will be 0, no? So now instead of fighting with the other things, no, I directly take help of Amperes circuit law. I'll call P1, P2, and P3. What about field at P1? 0. Field at P2, 0. Field at P3, non-zero. They may test you with questions like this. Of course, you know, but you must analyze with the Amperes circuit law. Draw Amperian path when Amperian path comes here. So when you draw like this, when it comes here, no, so net current elements enclosed will be 0, no, that's why field is 0. So what should be the condition for R? What is the condition for R? R should be less than B, greater than A. It should be within the limits of A and B. What are A and B? I'll introduce now. So this is A, this is B. So usually B will be comparable to A. This will be how much the diameter B minus A will come of few centimeters, like 10, 20 centimeter. Usually the inner radius is taken, the inner radius is taken the radius of the toroid. Very important. So any application problems do come, you must have basic this picture. This is very important. Okay, next we'll go for current carrying sheets. B bar due to current carrying sheet here.